Welcome again to the next part of this video presentation, where I'll be looking at the Northwest Regional Mock Proposed Solutions Pure Mathematics and Mechanics Paper 2 from question 6 to 10. In the previous video, I proposed solutions from question 1 to 5, and I promised to come up with the next part of the solutions. So doing the presentation, I'm Tata Ernest, and I'm going to be leaving video chapters because the video may be relatively long, and so that you can easily skip to that specific question that you face difficulties in. Without wasting a lot more of your time, let us begin. Question 6. Complex numbers and absolute value function. The complex number z is such that z is equal to what you are seeing on your screens right now. Express z in the form x plus iy, where x and y are real numbers. Find the argument of z, hence deduce at z raised to the power 6. So to begin with, I am going to write down the question. And what we can do here vividly is by simplifying this first term, because the denominator of that term is a complex number. And in order to simplify a complex number on the denominator, we need to multiply it by its conjugate. In order to obtain the complex conjugate of 1 plus I, we need to change the sign on the imaginary part. So the complex conjugate of 1 plus I is 1 minus I. So I'm going to multiply both the top and the bottom by 1 minus I. Then when I multiply it, I simply multiply these 3 by 1 minus I, and I multiply 1 plus I by 1 minus I. And 3 multiplied by 1 minus I is 3 minus 3i. Then when you multiply a complex number by its conjugate, then the result is a real number. So to obtain the result, I will just square each arm of the real and imaginary part and add them. The real part is 1, 1 squared is 1, and the imaginary part is 1, 1 squared is 1, and their sum gives 2. So I obtain this. Then I'm going to separate this numerator into two fractions to obtain 3 divided by 2 minus 3 divided by 2i minus 1. Then I add I. Then at this point, I have to bring the real part and the imaginary part together. So the real part here is 3 divided by 2 and negative 1. And the imaginary part is negative 3 divided by 2, then plus I. Then 3 divided by 2 minus 1 is positive half, and negative 3 divided by 2 to plus 1 is negative half I. So we have expressed the complex number z in the form x plus yi, where x is equals to half and y is equals to negative half I. The next question was to find the argument of z. Now, let me denote the argument of z by alpha. Then I'm looking for arg z, which is, of course, alpha. The argument of a complex number is the angle that the complex number line makes with a positive real axis. And that angle needs to be measured in the anti-clockwise direction and is not supposed to be more than 180 degrees or pi. So in order to find the argument of this complex number, I will represent this complex number on the Argand diagram. So this is the diagram here. I have the real axis, which is the x-axis, and the imaginary axis, which is the y-axis. Now on this complex number z, the real part is half. So I indicate the point half, and the imaginary part is negative half. I indicate the point negative half. These two complex numbers meet at this point, and so this is the line joining them from O. Now the argument is the angle measured from the real axis in the anti-clockwise direction. But if I take the argument like this, then it will be more than 180 degrees. So I have to reverse my direction and measure it in the clockwise direction. And also my argument would be negative because the direction has been changed. So this is, of course, the argument I am looking for. And alpha is that argument which is called to arg z. To obtain the value of alpha, I can find the ratio of the opposite length to the adjacent length. So I can use tan. Tan alpha gives me opposite length, which is half, divided by the adjacent length, which is half. So that alpha will be the tan inverse of the opposite length to the adjacent length. So I'll have negative tan inverse of half divided by half. Remember, the negative is because our direction for measurement of this angle has changed. So, and tan inverse of negative of half divided by half is 1, while tan inverse of 1 is 45 degrees. And expressing 45 degrees in radians gives pi divided by 4. Then we have the negative because we are multiplying it by negative 1. So the argument of this complex number is negative pi divided by 4. The next part of the question is to deduce arc z raised to the power 6. Now, from properties of argument of a complex number, arc of a complex number raised to a power is equals to n arc z. So I'm looking for arc z raised to the power 6. So I bring down 6 and I multiply it by the argument of z. So the result becomes 6 times negative pi on 4, which is negative 3 pi divided by 2. So this is the argument of z raised to the power 6. The next question, Roman 2, is find the range of values of x for which Mach 5 minus x divided by 2 plus x is equals to x minus 5 divided by 2 plus x. In order to solve this problem, we need to review the definition of absolute value function. So by definition, Mach x is equals to x if x is positive, and Mach x is equals to negative x if x is negative. So in order to solve this question, we have only two possibilities. We need to check if this value is positive or this value is negative of what is inside the absolute value sign. But then, if I take x minus 5 divided by 2 plus x and factor out a negative sign, I'll obtain exactly what is in the absolute value sign. That means Mach x is equals to negative x. And what is the condition for this? X should be less than 0. So the required inequality we have to solve is the inequality where x is less than 0. So this is what we are solving. And to solve this inequality, we need to start by finding our critical values. Critical values are the values for which 5 minus x and 2 plus x will give you 0. So 5 minus x is equals to 0 means x is equals to 5. And 2 plus x equals to 0 means x equals to negative 2. So negative 2 and 5 are our critical values. So we represent this on the sign table. I'll be drawing a number line and I will indicate the points where these critical values are. I have negative 2 and 5. So these three regions are the regions where I'll be checking the signs to see which region will satisfy this inequality. So let me start with the first region, the region where x is less than negative 2. I'll think of any value which is less than negative 2, say negative 4. Now I'll plug it into this expression and write out only the sign. 5 minus negative 4 becomes 5 plus 4, which is positive 9. And 2 minus 4 gives you negative 2. So I have a positive number divided by a negative number. So the result is negative. So taking any value less than negative 2, you have negative. Now in the second region, let me pick any value between them. Of course, 0 is the easiest value because there's a change in sign. So let me take 0. 5 minus 0 gives positive 5. 2 plus 0 gives positive 2. And positive 5 divided by positive 2 gives me a positive value. So any number I take between negative 2 and 5, I will be having a positive number. Now the last region, think of a value greater than 5. Let me think of 6. 5 minus 6 is negative 1, and 2 plus 6 is positive 8. Negative 1 divided by positive 8 gives me a negative value. So what were we looking for? We were looking for the range of value for which this expression is less than 0 or is negative. So these are the required regions. X is less than negative 2 or X is greater than 5. So, and this region is not required because any value between these two regions will be positive. So the solution set will be X is such that X is less than negative 2 union X is greater than 5. I hope you have understood this question. If you have a question or a doubt or a correction, please do leave it in the comment section below. Let's move on to question 7, which is a question on calculus. The first question is, let's find the integral from 0 to 1 of x e raised to the power x plus 2 with respect to x. The second question, we are asked to find the area enclosed by the curve y is equal to h of x, the x-axis and the lines x equals to 0 and x equals to 1, where h of x is equal to this function. And the third part of the question is, show that the gradient of the curve defined by x squared plus 2xy plus y squared is equal to 4 is a constant. Now, to begin with, let us look at some essential facts about the first part of the question. In this question, notice that x is not the derivative of e raised to the power x plus 2. So that means if I differentiate one of these functions, I cannot have the other function. So these are two functions where one is not the derivative of another. And when you are asked to integrate this type of functions, think of integration by parts. And integration by parts states that the integral of u dv is equal to uv minus the integral of v du. That means in the integral, you need to take one of the functions to be u, which you differentiate, and take the other function as dv, which you integrate. Now, your choice of u and v should be very, very, very important, because u should be in such a way that when you are differentiating, the power is being reduced so that your integral can be reduced into an integral which can easily be integrated. So I will take u as x and I will take dv as e raised to the power x plus 2. So u is equals to x. Then differentiating u with respect to x, I get 1. And dv by dx is e raised to the power x plus 2. And integrating this function will still give the same thing, because when I differentiate x plus 2, my answer is 1. And I have to multiply 1 by the function, which doesn't change its value. So I just apply the formula. So the integral of x e raised to the power x plus 2 dx is equals to uv. I take u and multiply with v, which is x e raised to the power x plus 2. Of course, I'm integrating from 0 to 1, minus integral from 0 to 1 of v du. This is v and this is du. I multiply, I get e raised to the power x plus 2 dx. Notice that here, the integral has been reduced to an integral which is easily integrated. So integrating e raised to the power x plus 2, I obtain the same thing that I had here, which is e raised to the power of x plus 2. So the common integration boundary are from 0 to 1. So I plug in the upper limit, I evaluate, minus the lower limit, and I evaluate. So if I plug in 1 everywhere I see x, I'll have 1 here, and 1 plus 2 is 3. So I have e cubed minus, I plug in 1 in this second function. So 1 plus 2 is 3. So e cubed minus e cubed. Then take away the lower limit. So I take 0 and I plug it into the entire function. And replacing x here with 0, this term vanishes. And replacing x with 0, I have 0 plus 2, that gives 2. So I have minus e squared. And this term gives 0, negative times negative gives positive. So that integral is simply e squared. So we are done with the first part. Let's move on to the second part. We are asked to find the area enclosed by the curve y is equals to h of x, the x-axis and the lines x equals to 0 and x equals to 1. and this is the function. What are we supposed to do here? Integration is literally finding the area enclosed by a curve, and it is found by doing a definite integral between the 2 points. So I will let a to be that area is equal to the integral from 0 to 1 of h of x with respect to x. Now h of x can be decomposed into the sum or difference of its partial fraction. So h of x is equal to a divided by 2x plus 1 plus b divided by x plus 1. Why am I decomposing it like so? Because these two denominators are linear, and therefore decomposing into partial fraction, the numerators needs to be a constant. So I have a constant a and a constant b. So you can solve this, you can solve for a and b using many other ways, but I will be using the cover-up method simply because the terms are linear, and now using that method will be the easiest method to use here. So using the cover-up method, how do I obtain a? I come to that term in a, then I find the critical value of this denominator. That is, I equate to 0 and I find x. Equating to 0, I'll have x is equal to negative half. So negative half is a critical value of this function. So a will be equal to, I come here and I cover up 2x plus 1 and I substitute negative 1 everywhere else, negative half everywhere else. I'll be able to obtain the value of a. So I have a is equals to negative half minus 1. I've covered up this, negative half plus 1. And doing the maths gives a as negative 3. To obtain b, I do likewise. The critical value of x plus 1 is negative 1. I come back here and I cover up x plus 1 and I substitute negative 1 everywhere else. So negative 1 minus 1 divided by 2 times negative 1 plus 1. Doing the math gives 2. So a is negative 3 and b is 2. So h of x can be expressed as negative 3 divided by 2x plus 1, then plus 2 divided by x plus 1. Integrating it now will be easy because I can separate it and integrate these two terms separately. So a becomes the integral from 0 to 1 of negative 3 divided by 2x plus 1 with respect to x, then plus the integral from 0 to 1 of 2 divided by x plus 1 with respect to x. In this first term, when you are given a fraction to integrate, the first thing you need to observe is that, does the derivative of the denominator give you the numerator? And if it does, then your answer is just ln of the denominator. But in this case, when I differentiate 2x plus 1, my answer is 2, but not exactly what is on the numerator. But I can do some constant adjustment. I can bring out this value, I divide by 2, and then I multiply by 2. So that when I differentiate 2x plus 1, I obtain 2. But I haven't changed the question because this 2 cancels out with this 2, and I come back to the same thing. I am just trying to adjust it in a way that I can have the integral easily. Then in this second term, I just bring out 2, and I have 1 divided by x plus 1. Now, the derivative of 2x plus 1 is equal to 2. So the first arm of the integration will be negative 3 divided by 2 ln of 2x plus 1. Then plus 2, the derivative of x plus 1 is 1, which is exactly the numerator. So I have 2 ln x plus 1 from 0 to 1. So I just plug in the upper limit and subtract the lower limit. So when I plug in 1 everywhere else, 2 times 1 is 2 plus 1 is 3. Negative 3 divided by 2 ln 3 plus, when I plug in 1, I have 2 ln 2. Then for 0, this term gives 0 and ln 1 is 0. 0 here, ln 1 is 0. So the answer is just 2 ln 2 minus 3 on 2 ln 3 square unit. That is the answer of this integration. Now, the third part of the problem is to show that the gradient of the curve defined by x squared plus 2xy plus y squared is equal to 4 is a constant. Now, how do we solve this? To solve this question, we need to see that this equation is defined implicitly. That means we cannot express y in terms of f of x. So we cannot make y the subject of the equation without having y on the other side of the equation. So in order to solve this type of a question, we have to differentiate implicitly. And we assume that y is equal to f of x, and we use the chain rule to differentiate the term. So let me recall the differentiation of product. If y is equal to uv, where u and v are of course functions of x, then dy by dx is I keep u constant, I differentiate v with respect to x, plus I keep v constant and I differentiate u with respect to x. So I am going to be applying this product rule in this differentiation. So to show that the derivative of this is equal to a constant, I have to show that dy by dx gives me a number. So this is the function, and I'll differentiate implicitly. So let me differentiate. To differentiate, you differentiate x normally, but since y is a function of x, when you differentiate y, you multiply the result by dy by dx. So we have, when I differentiate x squared, I have 2x. Then I have to use the product rule here to differentiate these two terms. 2 is a factor, I keep x constant, and I differentiate y, which is 1. And since it's a term in y, I multiply by dy by dx. Now I keep y constant, and I differentiate x. When I differentiate x is 1, and y times 1 gives y. Then plus, I differentiate y squared, that gives 2y, and because it's a term in y, I multiply by dy by dx is equals to 0. Because when I differentiate 4, my answer is 0. Now, let me open out the brackets. So I'm having 2x dy by dx plus 2 times y gives 2y plus 2y dy by dx is equals to 0. I'll bring terms in dy by dx together. So their coefficients is 2x plus 2y multiplied by dy by dx. I take this term in x the other way and this term in y the other way. So I have negative 2x minus 2y. Then at this point, I can divide both sides by 2x plus 2y, and I have negative 2x minus 2y divided by 2x plus 2y. Factoring out negative 1, the terms will cancel out, and then the answer is negative 1. So there's a negative sign here. I have shown that dy by dx is equals to negative 1, which is a constant. Therefore, the gradient of the curve is a constant. Now, question 8 is a question on vectors and proof. Question 8. With respect to the origin O, the point A, B, C have the position vectors as what you have on your screens, respectively. Find A, the Cartesian equation of the plane ABC. B, the sine of the angle BAC. First, we have to find the position vector of the point ABC with respect to the origin. So I'll be letting OA to be the position vector of this point with respect to the origin, I plus 2j then plus k. And OB to be the position vector of this second point with respect to the origin, while OC is the position vector of the point, this point with respect to the origin. So OC is negative I plus j minus k. Now, the Cartesian equation of a plane is in the form xi plus yj plus zk is equals to d. But we can use this vector form r dot n is equals to a dot n. R here is the general point, which is xi plus yj plus zk. N is the normal vector to the plane, where n is given by the cross product of the direction vectors AB and AC. So we are going to be using this equation in order to come out with the Cartesian equation of the plane. So, but an essential fact to note here is that the vector AB, or the direction vector AB, is equal to OB minus OA, and the direction vector AC is equal to OC minus OA. So we have to use this and obtain the direction AB and AC so that we can find the cross product of these two vectors and obtain the normal vector n. Now, AB is equals to OB minus OA. So OB is the vector 3, 3, 4. I'll write it in column form. And OA is a vector 1, 2, 1. Subtracting 3 minus 1 is 2, 3 minus 2 is 1, and 4 minus 1 is 3. So the vector AB is 2, 1, and 3. Then what about AC? AC is vector OC minus OA. OC is a vector negative 1, 1, negative 1, and OA is a vector 1, 2, 1. Subtracting negative 1 minus 1, that gives negative 2, 1 minus 2, negative 1, negative 1 minus 1, negative 2. So I have the direction vectors AB and AC. Next, I need to use this direction vector and find the cross product to obtain the vector n. Now, to find the cross product of this vector is similar to finding the determinant of a 3 by 3 matrix. So I'll be writing the component I, j, k here. Then I write the first vector, which is vector AB. I write AB as 2, 1, and 3. And the second vector that I'm multiplying by, AC, negative 2, negative 1, negative 2. Then the first term will be the minor of I. So I take I and I cross out the column and the row, and the resulting matrix will be what I'll be finding its determinant, which is 1, 3, negative 1, 2. Then the second term is always minus j. So I have minus j multiplied by its minor. So I cross out the column and the row. I have 2, 3, negative 2, negative 2, plus k multiplied by its minor, which is 2, 1, negative 2, negative 1. So at this point now, I find the determinant of this 2 by 2 matrix. So having I into, I multiply the elements of the leading diagonal minus the product of the elements of the non-leading diagonal. So for the I component, I'll have I into 1 times negative 2 gives negative 2, minus negative 1 times 3 gives negative 3, and negative times negative 3 gives positive 3. So that is why I have this. I do the same for the j component. I multiply 2 times negative 2, that is negative 4, then minus negative 6. So I'll be having negative 4 plus negative 6. Then finally, I have k into 2 times negative 1, negative 2, minus negative 2 times 1, negative 2. That gives negative 2 plus 2, which is 0. So the normal vector is I minus 2j plus 0k. Now, recall, let's use the formula r dot n, which r is the general point x, y, z dot the normal vector 1, negative 2, 0 is equals to a, and a is the position vector of OA. A, which is 1, 2, 1, dot n, which is the normal vector. So I multiply x times 1 gives x, y times negative 2, negative 2y, z times 0, 0 is equals to, I find the dot product of these two vectors. 1 times 1 is 1, 2 times negative 2, negative 4, 1 times 0 is 0. So I have 1 minus 4. So x minus 2y plus 3 is equals to 0 is the Cartesian equation of the plane. Now the next part is to find the sine of the angle BAC. That angle is the angle on A, and the angle on A is the angle between the direction vector AB and the direction vector AC. And of course, the formula for the sine of an angle between two vectors is the absolute value of AB cos AC divided by Mach AB Mach AC. And we only look for AB cross AC, and that is a normal vector n. So I'll just find the absolute value of n, and I look for Mach AB and Mach AC. Now, this is it. Let me substitute. I'm looking for the absolute value of n, then Mach AB. So I go to the vector AB and I find the absolute value, which will be 2 squared plus 1 squared plus 3 squared, all that square root, times Mach AC, which is negative 2 squared, then I add negative 1 squared, and I add negative 2 squared. This is supposed to be negative 2 squared. I'm sorry, negative 2 squared. And when we do the maths, it gives us root 5 divided by 3 root 14. So actually, this is supposed to be negative 2. That gives root 5 divided by 3 root 14. So you can go back and then try to evaluate this to verify the answer. The next part of the equation is to prove by mathematical induction that for every positive integer n, the sum from r equals to 1 to n of 2r minus 1 is equals to n squared. So we have to apply the principle of mathematical induction. And the principle of mathematical induction states that to prove by induction, you have to prove for the base case. In this case, the base case is r starts from 1. In some questions, r can start from 2. That means the base case in those questions will be n is equals to 2. But in this case, I'm starting from r is equals to 1. So that is the base case. Then when the base case is verified, you move on to the assumption case. That means you assume that the statement is true for some n is equals to k. You move now to the inductive step when you prove that it is true for its successor. That is n equals to k plus 1. And if this step is verified, then you draw a conclusion. Now, I will let Pn to be the statement that was given to me. Then on the left hand side, let me let n equals to 1, the base case. And if n equals to 1, I'm looking for the sum from r equals to 1 of 2r minus 1. So I just substitute r with 1. I have 2 times 1 minus 1, which is equal to 1. So you see that the left hand side gives me 1. For the right hand side, I just replace n with 1, and I'll be having 1 squared, which is equals to 1. So the statement holds true for n equals to 1. So the base case has been verified. Let me move on to the assumption step, which I'll assume that the statement is true for some n is equals to k. What does that mean? It means that the sum from r equals to 1 to k of 2r minus 1 is equals to k squared. Now I'll use this assumption in the inductive step. So the inductive step, I have to show that the statement is true for n equals to k plus 1. So let n equals to k plus 1. This is what I'm required to show. That is sum from r equals to 1 to k plus 1 of 2r minus 1 is equals to k plus 1 all that squared. I've substituted n with k plus 1 in the original equation. So this is what I have. So in order to show this, I will take the left hand side and show the right hand side. So the left hand side is equal to the sum from r equals to 1 to k of 2r minus 1, then plus the k plus 1 term. Remember, I'm summing from r equals to 1 to k plus 1. So I can sum the same expression from r equals to 1 to k, and I add the next term. Remember, k plus 1 is the direct successor of k. So I'll now sum from r equals to 1 to k, and now add the successor of k, which is k plus 1. And so that is why I have the sum from r equals to 1 to k, then plus the k plus 1 term, which I'll take k plus 1, and I plug it into this expression. That is why I have 2 into k plus 1 minus 1. And why are we even doing this? Because in the assumption step, we assume that this statement is true. So, and what was it? It's equals to k squared. So I'll just substitute all of this by k squared, and I'm having k squared plus 2k plus 2 minus 1. And this simplifies to k squared plus 2k plus 1. And this is a quadratic equation. Two numbers which multiplies to 1 and add up to 2. Of course, the numbers are 1 and 1. So I have k plus 1 into k plus 1 repeated factors. That gives k plus 1 all that squared. And that gives us exactly the right hand side. So since we have been able to show that it's true for n equals to k plus 1, we can now draw our conclusion. And the conclusion is that the statement is true for n equals to 1. Assuming true for n equals to k implies true for n equals to k plus 1. Therefore, the statement is true for all natural numbers n. Question 9 is questions on circles and matrices. Two circles S1 and S2 are defined by the equations. This is the equation of the first circle and this is the equation of the second circle. Show that S1 and S2 touch internally. Find the equation of the common tangent at the point of contact. Two circles touch internally if the difference between their radii is equal to the distance between their centers. So, in order to show that these circles touch internally, I need to find each of their radii and show that the difference or the distance between their radii is equal to the distance between their centers. And the distance formula is given by, let's assume that you want to find a distance between these 2 points, x1, y1, and x2, y2. So the distance between these 2 points is given by the formula x2 minus x1 all that squared and plus y2 minus y1 all that squared. And finally, the standard form of the equation of a circle is x minus a all that squared plus y minus b all that squared is equal to r squared, where AB is the center and R is the radius. So in order to show that these two circles touch internally, I will need to find their centers and of course find their radii. So to find their centers and their radii, I need to express each of these equations in the standard form of the equation of a circle. And how do I do that? I need to complete the squares in the terms in x and terms in y. So completing the squares for terms in x and terms in y on the left hand side, we are going to have, to complete the squares, you need to ensure that the coefficients of x squared and y squared are 1. And in this case, they are all 1. So we move on to the next step, which is taking half of the coefficient of x and the coefficient of y, squaring it and adding it to both sides. So what is half of the coefficient of x? Half of -4 is -2. I'll square that term -2 and add to the left hand side and also to the right hand side. So I take also half of the coefficient of y. Coefficient of y is -6, half is -3. I square it and I add it to the left hand side and also to the right hand side. So doing that will ensure that the left hand side is now a perfect square in terms in x and a perfect square in terms in y. So computing the squares now, I'll just have x minus 2 all that squared, then plus y minus 3 all that squared is equal to, simplifying all terms on the right hand side will give 1. So I have expressed S1 in its standard form. So in this case now, the center of this circle will just be the critical values of the term x minus 2 and y minus 3. So the center is the point 2, 3, and the radius is the square root of 1, which is equal to 1. Similarly, S2, I compute the squares for terms in x and terms in y. Half of -4 is -2. I square and I add to both sides. Half of -8 is -4. I square and I add to both sides. So this is what I have. So I'll be having this equation on the board. So the left hand side now, the squares have been completed. So I'll be having x minus 2 all that squared, then plus y minus 4 all that squared is equal to 4. Now the center of the circle is a point 2, 4, and the radius is the square root of 4, which is equal to 2. To show that they touch internally, I'll need to find the difference between their radii and compare it with the distance between their centers. And the difference between their radii will just be, I'll take the radius of the first circle, which is 1, minus the radius of the second circle, which is 2, and the result is -1, so the distance between them is +1. And finally, I'll find the distance between their centers, C1 and C2. Using the distance formula, I'll be having 2 minus 2 all that squared. I add it to 4 minus 3 all that squared. Doing the math gives me the square root of 1, which is equals to 1. Since the distance between their radius is equal to the distance between their center, as 1 is equals to 1, I conclude that S1 and S2 touch internally. To find the equation of the common tangent at the point of intersection, we need to find the difference between the equations of the circles, that is, S1 minus S2, or S2 minus S1. Subtracting them, this is the equation of the circle S1, and this is the equation of the circle S2. I will subtract them algebraically. X squared minus x squared, 0. Y squared minus y squared, 0. Negative 4x minus negative 4x, 0. Negative 6y minus negative 8y gives negative 6y. Positive 8y, which gives you plus 2y. Then 12 minus 16, negative 4 is equal to 0 minus 0, 0. So taking negative 4 the other way and dividing both sides by 2 will give y is equals to 2 is the required line. So y is equals to 2 is the equation of the common tangent at the point of intersection of the circles S1 and S2. Now, the next question is on matrices. We have been asked to find the inverse of this matrix, and hence we solve the system of equations that follow. The inverse of a matrix M is denoted M inverse and is equal to 1 divided by the determinant of the matrix M multiplied by the adjugate of M, where adjugate of M is the transpose of its cofactor matrix. So to find the adjugate of a matrix, you need to find a matrix formed by its cofactor and transpose that matrix. You'll be having the adjugate of the matrix. Now, let us start by finding the determinant of this matrix. The determinant mark M is equal to, the first row over here is 0. So I take 0 and I multiply it by its minor determinant. So how do we obtain the minor determinant of 0? I cross out the column where 0 is and cross out the row. Then I'll have this resulting matrix, which is 1, 2, negative 1, 2. So I'm finding the determinant of this matrix to obtain the result. Then I will always attach a negative sign to the next member or element of that matrix. So I have negative 2 multiplied by its minor determinant. I'll cross out the column and the row, and the resulting matrix is 3, 2, and 3, 2. Then positive 1 multiplied by the minor determinant of 1, cross out the column and the row, and I have the resulting matrix, which is 3, 1, 3, negative 1. So how do we find the determinant of a 2 by 2 matrix? I multiply the elements of the leading diagonal minus the product of the elements of the non-leading diagonal. So of course the first term will vanish because 0 multiplied by whatever will give 0. So I have negative 2, here is negative. Then this 3 times 2 gives 6, minus 2 times 3, which is 6. And 6 minus 6 is 0. Plus 3 times negative 1 is negative 3, minus 1 times 3, which is 3. And so the determinant of the matrix M is equal to negative 6. We need to know the associated signs of each cofactor element. So in a 3 by 3 matrix, this is the convention. This is the signs that each cofactor matrix is going to be associated with. So when you find the minor of each element, to obtain the cofactor, you have to multiply it by its associated signs. So let me begin with adjugate of M will be equal to, I will cross out, I'm looking for the minor or the cofactor of 0. So I cross out the column and the row as I did before. and the resulting matrix will be 1, 2, negative 1, 2. Then I need to multiply this determinant by its associated sign to obtain the cofactor of 0. So I'll be having positive multiplied by this determinant, which will give me the minor of 0. Then I proceed. I go to the next element, which is 2, cross out the column and the row, and I multiply the resulting matrix by negative. I move on next element, which is 1. I cross out the column and the row, and I multiply the resulting matrix by its associated sign, which is positive. Then I do like that for each and every member in this matrix. So I'll be having these resulting cofactor elements. Then at the end, I will transpose this matrix in order to find the aggregate of M. We have already seen how to find the determinant of a matrix. So you just multiply the elements of the leading diagonal minus the product of the elements of the non-leading diagonal. So doing the multiplication, I'll obtain this matrix. Now, finding the transpose of this matrix, which is interchanging the rows and the columns, I will be having the first row becomes the first column, the second row becomes the second column, and the third row becomes the third column. So this is the transpose of this matrix. And this matrix is the aggregate of M. So M inverse is equal to 1 divided by its determinant, negative 6, multiplied by the aggregate, this matrix over here. So we have looked for the inverse of M. Now, how can we use the inverse of M and solve this system of equations? First things first, I need to rewrite this equation in matrix form. So, and the elements of this matrix will be the coefficients of x, y, and z in that order. The coefficient of x in the first equation is 0, the coefficient of y is 2, the coefficient of z is 1. Coefficient of x is 3, coefficient of y is 1, coefficient of z is 2. Coefficient of x is 3, coefficient of y negative 1, coefficient of z 2. Then I multiply by x, y, z because that is the order in which the terms appear in all the equations. And I equate it by the matrix formed by their result, 5, 13, and 9. Let M be equals to this matrix. And then notice that this M is the same as the matrix that we had looked for the inverse. Now let me call a matrix X to be the values, the matrix formed by X, Y, Z, and let X prime be equals to the matrix formed by their result, 5, 13, and 9. Now, so I'll be having M, which is this matrix, multiplied by the matrix X is equals to X inverse. Then how do I obtain X, what I'm looking for? I multiply both sides by the matrix M. To be precise, I pre-multiply by M inverse. So when I multiply by M inverse, I have M inverse times M times X is equals to M inverse times X prime. I'm pre-multiplying, so do not change the order because matrix multiplication is not commutative. Now, a matrix multiplied by its inverse gives you the identity matrix. So I have Ix is equals to M inverse times X prime. And the identity matrix multiplied by any matrix of the same order will leave the matrix unchanged. So I times X gives you I. So what we have to do is just to take the inverse of M and pre-multiply the right hand side of this equation. So X will just be M inverse times the matrix X prime. So we have M inverse already. So X will be M inverse times X prime, which is equal to the inverse of M is negative 1/6 multiplied by this matrix, and I multiply by the matrix 5, 13, and 9. So I will leave the negative 1, 6 outside, and I multiply. I will take this first row, multiply by the first column. 4 times 5 is 20, negative 5 times 13, negative 65, and 3 times 9 is plus 27. And I take the second row and multiply by the column. 0 times 5 is 0, negative 3 times 13, negative 39, and 3 times 9 plus 27. And finally, negative 6 times 5, negative 30, 6 times 13 plus 78, negative 6 times 9, negative 54. Now adding the numbers, I'll have negative 1 sit into negative 18, negative 12, negative 6. Let me now multiply this matrix by this scalar. So negative 1 over 6 multiplies into this matrix, or I'm dividing each term by negative 6. So I'll have 3, 2, and 1. That means the value of x is 3, the value of y is 2, and the value of z is 1. You can go ahead and verify these values in this equation just to be sure that these answers are correct. Now question 10 is sequences and series and curve sketching. Show that the sum from 1 to n of 2 into 1/3 raised to the power r minus 1 is 3 into 1 minus 3 raised to the power negative n. We want to show that if we sum the terms, of this sequence, we will arrive at this result. Now, in order to proceed, let me write out some few terms in this series. R starts from 1, so I'll substitute r with 1. So I'll be having 2 into 1/3 raised to the power 0. R moves on to 2. I have 2 into 1/3 raised to the power 2 minus 1, which is 1. And r goes to 3. 2 into 1/3 raised to the power of 3 minus 1, that gives 2, and it continues because I'm summing till a finite number n. But I will stop here so that I can be able to see if the terms have a particular pattern. If I can draw out a pattern, and of course I want to find out if the terms form a geometric progression or they form an arithmetic progression. Now 1/3 raised to 0 is 1, so the first term is just 2. Then I have 2 into 1/3 raised to the power 1 plus 2 into 1/3 raised to the power 2, then plus it continues like so. Now looking at it keenly, I will see that of course there is a pattern because 2 is common to each of the term and 1/3 2 appears. That means, and if I find the ratio of any two adjacent terms, I will have a common ratio, which is 1/3. Because if I take the second term and I divide it into the first term, 2 strikes out with 2, I have 1/3. If I take the third term and I divide into the second term, 2 strike with 2, square takes care of 1 of the 1/3 and have 1/3. So I can conclude that the terms form a geometric progression with the first term as 2 and the common ratio as 1/3. So they're basically asking me to find the sum of this geometric progression. And the sum of a geometric progression is given by the formula a into 1 minus r to the n divided by 1 minus r. A is 2 and r is 1/3. If I plug in the value, I'll have 2 into 1 minus 1/3 raised to the power n divided by 1 minus 1/3. And 1 minus 1/3 is 2/3. So, and simplifying this, 2 cancels out with this 2, and this 3 reciprocates, and I'll be having 3 into 1 minus 3 raised to the power negative n. And our answer is out because we can rearrange it now into 3 into 1 minus 3 raised to the power negative n as required. So we have shown that. The next question is to sketch a curve 1 divided by x squared minus 4, where x is different from plus or minus 2, of course. And we have to show the intercept, the asymptote, and the turning point. So these are the 3 key features of the function that we need to represent. Now, to sketch a curve, the following properties of the function has to be investigated. The first and perhaps the most important is the domain of the function. So this is simply the set of values of x for which the function is valid. So the next information is the intercept. Where does the curve cut the y-axis and where does it cut the x-axis? The next is the asymptote. And there are basically 2 asymptotes, vertical and horizontal. we need to investigate them. Then the turning point, of course, where does the curve turn? And is it a maximum turning point or a minimum turning point? And we have to represent that on a variation table, though it's optional. But this table is very useful because it helps us sketch our graph very easily. And finally, we can sketch our curve. It's true that you can investigate more than just these properties, but for pure mathematics, we limit ourselves to just a few. So these properties will be enough for most of the curves that will be given to us. So the function is 1 over x squared minus 4. Notice that the denominator can be written as the difference of two squares. I can write this as x squared minus 2 squared, which can be rewritten as x minus 2 into x plus 2. Now, the domain of the function, which is, of course, the first property we have to investigate, let's call that d of f. The domain of the function was even given in the question already, because the function can take all real values except two elements, which is plus 2 and negative 2. So the domain of the function is a set of real numbers except these two elements, plus 2 and negative 2. Now we can write it in this interval notation form, which is very important. So the domain means the values of x will leave from negative infinity and take all values and end at negative 2. So negative 2 is not included. That is why at this point it is open. Union, it starts at negative 2 and ends at 2 because 2, of course, is not included. And then union, it takes from 2 right up to positive infinity. So I have basically these three intervals are the intervals that I need to sketch the curve on. Taking note that negative 2 and positive 2 are the points, are the values of x for which the function is undefined. Now moving on to the intercept. The equation of the x-intercept is the line y is equal to 0. So if I substitute y as 0 in this function, so f of x is 0, then this denominator vanishes and I cannot find a value of x. So there's no x-intercept. That is, the graph does not cut the x-axis anywhere. What about the y-intercept? The y-intercept is the line x equals to 0. So I equate x with 0 and I'll be having 1 divided by negative 4. So the y-intercept is the point 0, negative 1 all over 4. Now, let's start with the vertical asymptote. The vertical asymptote are simply the point that the graph is undefined. Like in this case, we just equate the denominator to 0 and we are going to have two values, negative 2 and 2. And notice that the vertical asymptote can easily be obtained from the domain of the function. That is a point where the function is not defined. Now, the horizontal asymptote, we find the limit of the function f of x as x tends to infinity. That is the limit of this function. So how do we find the limit of this function? One of the ways is to divide each term by the highest degree in the expression. And the highest degree is x squared. I divide each term by x squared. I'll have 1 divided by x squared. X squared divided by x squared gives 1 minus negative 4 divided by x squared. Why are we doing that? Because we know that as the denominator becomes very large, the number is turning towards 0. So this number turns towards 0 and this number turns towards 0. And 0 divided by any value gives us 0. So the line y is equal to 0 is the horizontal asymptote. What about the turning point? To obtain the turning point, we need to find dy by dx and equate to 0 and solve that equation. So dy by dx will be equal to, I'll use the quotient rule to differentiate, bottom x squared minus 4 multiplied by the derivative of the top 0 minus the top 1 multiplied by the derivative of the bottom 2x divided by the bottom squared x squared minus 4 all that squared. This term gives 0 and I have negative 2x divided by x squared minus 4 all that squared. So this is the derivative function or the gradient function of f of x. Now, dy by dx is equals to 0 means I equate this to 0 and solve for the value of x. Equating to 0 and solving, I'll be having this term vanishes to 0, and I'll have negative 2x is equals to 0. That means x is equals to 0. So y is equals to negative 1 divided by 4. So hence the point 0, negative 1 over 4 is a turning point. And notice that this turning point is the same point as the y-intercept. It is just a coincidence. It must not be so. So we have a y-intercept, and at that point the curve is turning. So now that we have investigated the most important properties of the curve, let's move on to sketch the curve. This is a domain of the function. This is the y-intercept. This is the vertical asymptote, -2, the lines x equals to -2 and 2. And the horizontal asymptote is the line y equals 0. Now we have the turning point. The point 0, -1 over 4 is a turning point. And then we have to draw the variation table. So this gradient function, dy by dx, which is -2x divided by x squared minus 4 other squared, will help us to draw a variation table. So on the variation table, there are 3 rows that need to be drawn. The first row is going to indicate the values of x. That is, you just represent the domain on the first row. The second row will be the gradient function. What will be the sign of the gradient? And of course, the third row will be the function itself. How would the graph look like? Now, for the gradient function, for the domain, you see that the domain is x starts from -infinity and comes up to -2, then, which is a vertical asymptote, and then from -2 to +2, which is another vertical asymptote, and finally from +2 to +infinity. Then the next thing is that these are vertical asymptotes. I'll use solid lines to show that the graph cannot cut through the vertical asymptote. And now the next thing is that I have between -2 and 2, I have a very important value, which is a turning point, because at the turning point, the value of x is 0 and y is -1 over 4. So I'm writing only the value of x, so the turning point is at 0. So I will start with the gradient function, f prime of x. This is a gradient function. So I will take any value of x between -infinity and -2. Let's take -5. If I plug -5 here, -2 times -5 gives positive. Squaring any number makes it positive. So I'll always have positive for any value between this interval. So within this interval, the gradient function is increasing. Now, at the turning point, I can draw a line and a circle to show that the graph is turning at the point x equals to 0. Then I also investigate if the graph is increasing or decreasing between these two sections. So let me take a value between -2 and 0, say -1. If I plug it here, I'll have positive. Now let me take a value between 0 and 2. Let me take 1. -2 times 1 is -1. So I have a negative value. Now taking a value between 2 and infinity, 5 for example, I have negative. So I have the signs of the gradient function. So between -infinity and -2, the graph is increasing. Between -2 and 0, the graph is increasing. Between 0 and 2, the graph is decreasing. And between 2 and +infinity, the graph is decreasing. So I can now go to the shape of the graph itself. That means f of x will be increasing from the horizontal asymptote. It means that it will be increasing from the point 0 to +infinity, because it cannot cross this other line. So on the graph, then at this other point, the graph is increasing from -infinity right up to that turning point, which is -1 all over 4, and then decrease, because it's a minus, decreases to -infinity. Then finally, on the last section, the graph will be decreasing from a +infinity, because this is a vertical asymptote, right up to the point 0. And on the right hand side, we have our graph. So this is a graph that we have. So we have between negative infinity and 2, the graph is decreasing. The graph is increasing from 0 to positive infinity. Now between negative 2 and 2, there's a turning point at the point x equals to 0, and the graph decreases, and the graph increases from negative infinity to that 0, and then decreases from 0 right down to negative infinity. Then the last section between 2 and infinity, the graph decreases from positive infinity then to the horizontal asymptote 0. I hope you have learned a little bit from this presentation. So we have come to the end of the presentation. So you who have watched the video to the end, I'll be leaving links where you can download a handout of all the solutions, and you can go through, then ask questions, and so that you can understand more better. And also, I'll be leaving a link as well that you can propose questions. If you have a question that you have difficulties in, you can send me the questions and I'll solve. Then I'll be able to reply to your question. So make sure you send it as quickly as possible, because I'm going to be attending to those questions in order that they were sent. Now, we have come to the end of the presentation, but if you do have any questions, then leave them in the comment section. I will look at the questions and reply you. And if you have any recommendations for future videos, like I said, I'll allow a link where you can send questions or difficulties, and I'll be able to look at them and respond to those questions. Then if there are some corrections or criticisms in the presentation, feel free to tell me. To err is human. We can always make mistakes, and we learn every day. So you can just tell me where I am wrong, or some questions that I have not solved it the way you really wanted, and I'll be happy to receive those criticisms. Then you can leave your comment as well to encourage me to produce more videos like this one. And thank you so much for watching to the end, and you all have a wonderful day.